Hi, so in this video we are going to be looking at the representation theory of a finite group. The finite group we are going to be looking at is the group D3. So this is the dihedral group of order 6, and it consists of 6 elements. Element I, which is clearly the identity element, an element A, an element B, an element A, B, an element BA, and an element A, B, A, where it's useful to note that A, B, A is equal to B, A, B, and then there are some other interrelationships. So A is its own identity, B is its own identity, AB is the inverse of BA, and vice versa, clearly, and ABA is its own inverse. So it's worth checking. Well, okay, I'm telling you this is a group. I'm not going to check it explicitly, but it's worth, at this stage, just writing down actually what a group is. So let's write down the requirements for this to be a group. Firstly, it must be closed. Okay, so that is one of the first things a group must be, and it has to be closed. It also has to have a multiplication on it, and that multiplication must be associative. My spelling is probably wrong, but associative means that if A times by B times by C like this is equal to A, B times by C. It also must have a left inverse, which means that for every element A, or for every element G rather, there's an element G to the minus 1, so that this is equal to the identity element, and it also must clearly have an identity element, or actually it only needs to have a left identity, and I'll explain this in a minute. So it only has to have a left identity, and that is defined such that AGI is equal to I, that is equal to G for all G in G, where G is the group. Okay, so here technically this should probably be 3 if I'm being really fussy about this as a 4, because 3, or because this one relies on the fact you have the identity. And then so now you'll notice here that I have put left, so left identity and left inverse. Sometimes you see definitions of groups without that. It's actually the case that having a left inverse and a left identity immediately implies you have a right inverse and a right identity, and that the right identity and the right inverse is the same as the left inverse, and the right identity is the same as the left identity. So these two conditions give the standard group, although they're slightly less strict. Okay, so we'll now get on to something called conjugacy classes. Conjugacy classes. My spelling again is probably wrong. Conjugacy classes. Okay, so what is a conjugate class? It is a set of all elements. Okay, so the conjugacy class of A, so we'll write it. So let's take an element G in G, and then the conjugacy class of that, I'm going to just write this for now, is equal to the set of all elements, so let's call it H, within G, given that G prime H times by G prime G prime to the minus 1 is equal to H for some G prime in G. Okay, so that's conjugacy class, and we can find the conjugacy classes of our group here. Now, I chose this example for a specific reason, and that is it is non-arbene. So arbene means it's commutative because I'm not identifying these two elements. And that means, so for an arbene group, the conjugacy class is quite trivially, actually just the element itself. But in our case, we have to do some work. So let's try and find the conjugacy classes. It turns out that I is always in a conjugacy class by itself. Should be clear from this relationship. If you have that, then if you have I here for G, then the only element you can get out is I, because G prime times by G prime to the minus 1 by definition is I. So let's try and find the conjugacy classes of A. Okay, so we'll start by the easiest case. We'll start by doing A times by A times by A. Remember I said that A is its own inverse. So this gives A. That just tells us that A is in its own conjugacy class. Okay, let's try B times by A times by B, and that is actually ABA, which I said up here. That is kind of like a relationship that helps define the group. And we'll also take that A times by B, A. This is equal to A B times by AA, which is equal to B, because this is the identity and this is the identity. And then lastly, or actually no, not lastly, because we've only checked one of these here. So we have to check BA times by A times by AB. That turns out to be BAB, which is this up here, which is ABA. Let's see if I can scroll down a bit. Okay, that was too far. So now we have this relationship here. We can test. We have one more to check. If I can get my pen back. Okay. So let's just check the following: A times by ABA. So if I do brackets, we do that. Doesn't matter because multiplication is associative. We'll do this A times by this A gives the identity, which gives us A B A B A. And if we look up, I think that's there, so that's equal to B. So here we have another conjugacy class. Notice that we have, I'll highlight the unique elements, or underline the unique elements. We have A, ABA, and B. So this is our second conjugacy class. We have A, B, and A, B, A. Okay, now we could go and work out the conjugacy class of B, but we will not be surprised to find we get the same thing, and we could also find out of ABA. I would also get the same thing. That makes our life much easier because it immediately reduces the number of calculations we have to do. So we then go on to finding the conjugacy class of AB. We do this the same as follows. We do A first. We go ABA times by A because A is its own inverse. And then this identity goes to here, and we get that. But now we've actually counted for all elements, because we have AB and BA are in the same conjugacy class because of this relationship here, and this went down here, and AB, I should probably mention AB is clearly in its own conjugacy class because of that relationship. So this gives us our last conjugacy class, and I'll write all the conjugacy classes down so we have an easy place of reference. I will call that one C1. Actually, no, let's call that one C0. We call the following AB ABA. We'll call this one C1, and we'll call the last one, which is AB BA. We'll call that C2. Can't draw an equal sign. Okay, so we now have that, and we want to find the dimensions of the representations, or the dimensions of the irreducible representations. So dimensions of irreducible reps. So this means dimensions, this means irreducible representations. That's standard abbreviation. The thing we use is that, first of all, the number of irreducible reps, technically complex irreducible reps, is equal to the number of conjugacy classes. And that means we have 3 conjugacy classes, so we have 3 irreducible reps. We know one of them has to be the trivial rep, so one of them we have already, and that has dimensions equal to 1. And then we also have the relationship that the sum of the dimension squared must equal the order of the group, which in our case is 6, because it's called a dihedral group of order 6, even though it's donated D3. So now we have that relationship. We know that one of these has dimensions 1, so let's put summing from I equals 0 to 3. We know that R0 has dimensions 1, so we must have the dimensions of R1 squared plus the dimensions of R2 squared must equal 5, and then clearly if we define R1 to have the lowest dimension, that clearly has dimension 1, and that clearly has dimension 2, not 4, 2. So now we have that, we can start to find what's called the character table. So the character table helps kind of like uniquely specify the irreducible rep. So we have we start with the character table like this. Put the Condors classes up here. I just thought of a question. I'm wondering now if you can have the characters of two irreducible representations being the same. I don't think you can, but I'm not sure of a proof about that. But that's an interesting thing to look up. Okay, so this is our character table. We have the characters in these columns here. We have the representations down here, and we know that every element of a given Condors class has the same character, so we only need to look at the Condors classes. The irreducible rep, the trivial rep, has character 1 in all of them. This is the rep with the identity, so this has character equal to the trace. By the way, I should mention the character of an element G in a rep R is just the trace of RG, and because this is two-dimensional rep, that should be 2, the identity maps to the identity, the trace of the identity is the dimension of the rep, this is 2. Okay, so now let's look at how to fill the rest of this table. So this is kind of non-trivial actually, because we have like these 4 empty spaces. If we can fill this R1 row, we can get the R2 row, but it's how do we fill this R1 row, which is the challenge in this question. Well, not question, in this like finding the character table. And we do that by noting that we require that R1A squared must equal R1 times by identity must equal 1. We also have that R1 times by B squared has to equal 1, and also that R1 times by A times by R2, R1 times by B must equal 1. And that actually tells us something. That tells us that R1 times by AB must equal 1. And that gives us this column here. That means we put a 1 there. So this is because that RAB is in R2. Now we have that R1A can be plus or minus 1. Now if it's plus 1, that's the same as the trivial rep. In this case it clearly is, because it's a one-dimensional representation. So we have to have minus 1, and thus we put a minus 1 there. To get this bottom row, we use orthogonality. You can use orthogonality of the rows or the columns. It's not quite orthonormality. For orthonormality, you have to take account of things like 1 over times by the order of the group factors. But you can actually convert this into a unitary matrix, which helps. But we can do it simply. if we take the dot product of this column with this column, we must get 0. That means that this, because 1 minus 1 is 0, this must be 0. And then dotting this with this, that is 1, 1, 2. So this needs to be minus 1. So this is our character table. And we can go further. We can write down the one-dimensional irreducible reps because they are the one-dimensional irreducible reps. And the last thing I'm going to do in this video is find the projectors. So the projectors onto phi just by the dimensions of Ri squared. Okay, so this is part of the irreducible rep, and to be honest, because I'm kind of getting bored, I'm just going to write them down. So the projector of R0 is 1 over 6, because you have dimensions. So this is dimensions of the rep, this is the order of the group, and then we just times character table. So this is going to be I plus A plus B plus AB plus BA plus ABA, and then our projection for R1 is 1 over 6 times by I times by minus A minus, not times by, let me say minus A minus B minus ABA minus plus AB plus BA, and then for P2 we get 1 over 3, that's because 1 over 3 is 2 over 6, I minus 0 minus 0 minus 0, or plus 0 plus 0 plus 0, plus AB minus minus AB minus BA, and just for laughs I'm going to put 0 there. Okay, so they have the projections of that. As well as that is as much as you can do easily. You can find the two-dimensional representation by looking at this projector, then acting that on basis elements, and then going from there. That is non-trivial. I've done it actually for this group, but you have to block diagonalize a matrix, which is possible but not easy. I kind of did it by guesswork. So that's the end of this video, and I hope you've roughly learned at least something. Okay, thank you.